All right, you guys. So, centripetal motion. It's not like you're ignorant of this. You have some concepts behind it. I just want to kind of refine some things and make you think about it a little bit. What words not to use, and certainly things never, ever, ever to use in a problem. So, first and foremost, the basics. Anything traveling in a circular path, circular. That means traveling in a circle, not a parabola, not an ellipse, but a circular path is being held in that path by what's known as a centripetal force. That centripetal force is always, 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 always acting towards the center. Now, one of the things that's fairly important is that you understand that while there is a centripetal force holding it to the center or keeping it in this curved circular path, there is no such thing as a centripetal force. In other words, never, ever, ever, ever do you ever label something FC. That's a no-no. Never do it. There's no such thing. There are forces that act as centripetal forces. There are forces that hold objects in a circular path, but there's no one special thing called a centripetal force. Centripetal forces come in many flavors. They could be a magnetic force. They could be a string. They could be friction. They could be a surface. They could be all kinds of things, and they are the things that act towards the center of the circle, but no one such thing is called a centripetal force, okay? A couple other things about this. When we talk about centripetal forces, we're still talking about Newton's second law, right? When you hear the term forces, you should think Newton's second law. And again, this vector sign over the top is fairly important. What that means is, if there is a net force towards the center, whatever that net force is, that also means that the acceleration is in the same direction. In other words, it is a center-seeking acceleration. That's kind of hard for people to get their heads wrapped around, because this kind of acceleration is a little bit different. Acceleration, remember, is a vector, and it is the difference between the initial and the final velocities, which again are vectors per unit time. Typically, when you guys have played with this, it's been the change in this part, the change in the speed, right? You speed up, you slow down, well, there's an acceleration. And that's linear, right? That's translational. But what you can also do is change this part, meaning the direction. And that's literally what's happening when we talk about centripetal acceleration. This thing travels along at a constant speed, and its speed never changes. But remember, velocity is speed with direction. And while these guys may have the same magnitude, it may be traveling 10 meters per second the entire way around this. So its speed never changes. What is changing, its velocity. And very simply, this guy is going in this direction. This guy's going in this direction. This guy's going in this direction. This guy's going in this direction. So the change is in the direction, not in the speed. It's not speeding up or slowing down. To achieve that change in velocity, you have to have this centripetal force. And that's why the acceleration is also center-seeking. Now, this acceleration, oftentimes, I think last year you guys put AC for centripetal, because it is a special case that we're talking about. And it can be calculated by saying V squared over R, right? Where R is the radius of the circle, and V is the speed. So if you know the speed of this sucker, and you know how big the circle is, you can figure out how big of a force it takes to hold it in the circle, okay? So I'm going to go through a couple of things with you guys, a variety of cases that you might see, just to make sure we're all on the same page, okay? One other thing, there is this force that people like to talk about that is the ultimate F word in physics, and that word is centrifugal. And this is about the only time you'll hear me curse, right? A centrifugal, notice that is not tripetal. I'm not talking centripetal, centrifugal. Centrifugal is a made-up force. And the centrifugal force is a force that points outward. Oftentimes people say, oh, when I turn the curve in my car, I get thrown to the outside of the curve. Or when I'm on an amusement park ride, I get held to the wall. Well, this force is called a pseudo force. It's not something that you should ever use in any of your descriptions, nor should you ever draw it on a force diagram. Period. The end. It is our perception of what's happening to us. It's our human ignorance making up this force. It's a fairy force. It's something that we are ignorant about and we feel it. So by our feelings, we give it a name. Some engineers are taught to use this. Don't you? I mean, when you become an engineer, do what you want. But while you're in physics class, while you're in here with me, this is not something that you ever put on a force diagram because it doesn't exist. Which brings me to the last thing. When you're looking at these situations and you're struggling to figure out what force is acting, if you can't name that force, for goodness sakes, don't put it on there. Put on forces that you know, and then you'll be fine. But if you start putting on these extra forces out here, boom, you're going to be in trouble. Okay, that's all the preaching I'm going to do and all the cursing I'm going to do with that word. So let's look at the first couple of examples. The first example is the one I like to use that you guys kind of did last year. You take a ball and you put it on a string, right? And you spin it in a circle. Boom. So it's traveling in this direction here. It's traveling in this direction here with a velocity in this direction, with a velocity in this direction, and we'll say it has mass m. And the radius of the circle is r. And one of my favorite questions is, okay, what's the tension here and what's the tension here? Now this thing is spinning in a circle, right? So let's just look at the forces that are acting on it, and let's draw the force diagram, right? So up here at the top, you certainly have mg pulling down. And you also have tension pulling down, right? Both of those are acting in the same direction. Let's look down here. You've got mg still acting down. But this time you have the tension upward. Now, a couple of things I need you to look at before we start doing anything. In this case, the forces are fighting each other. In this case, the forces are working together. You see a circle. So immediately in your mind, you need to say to yourself, this thing is traveling in a circle. It has to have a net force that's acting towards the center. This case is pretty easy. So let's use Newton's second law, right? Here we go. Who's winning the tug of war? These two guys. So they're the net force. And that is equal to m times a. But now the a that we're talking about is our centripetal acceleration. V squared over r. Let's look at the one in this case. Now we've got a different situation. And a lot of people like to say that these forces are equal, but they can't be, because it would just travel along in a straight path and keep going. Somebody has to be winning the tug of war if it's held in a circle. In your mind, you should think circle, center-seeking force. This is what points towards the center, therefore it must be winning. So our Newton's second law here is going to be, this guy's winning the tug of war over this one, so it's T minus mg is equal to, but we're going to use the same thing, centripetal acceleration, V squared over r. Okay, you could find out very quickly the tension. So up here the tension would be equal to m V squared over r minus mg. And we could do the same math game down here. It would be T is equal to mv squared over r. But in this case, it's plus mg. Now, I'm using this simple example to show something kind of significant. The velocity is the same in both cases. The radius is the same. The mass is the same. Where is the tension the greatest? Or what I like to ask is, where is it most likely to break? Well, if you look at the tension, this has got a plus sign. And it's because these two guys are fighting against one another. So tension has to work that much harder to hold it into the circle, as well as fight against gravity, fight against the weight. So it's most likely to break down here at the bottom. Look up here. both of these two forces are holding it in the circle, right? And so tension doesn't have to work as hard because gravity is doing some of the job as well. That's why up here it's subtraction, and that's why this tension's a little bit less. What I want you to see is the overall process. What did we do? We drew a force diagram first. We found the net force, always thinking that it's got to be towards the center. This one's pulling towards the center. This one's pulling towards the center. Then we set it equal to ma, where in this case it's our centripetal acceleration. So you can solve, you can find anything, okay? First case scenario. Second case scenario is the one you guys don't like so much. It involves gravity. So let's say that I have the Earth here. And let's say that I have a satellite, call it S. And it's going to travel around in a circular path, okay? It's not so circular, but cut me some slack. And let's say it has a radius r. All right. Again, your job is to figure out, okay, what forces are acting on it. Let's give it a mass too. We'll call this me for the mass of the Earth, and we'll call this ms for the mass of the satellite. Your first job is to draw a force diagram. All right, here's our satellite. And it's being held in a circular path. So automatically you should be drawing a force inward. And in this case, it's the attraction, gravitational attraction between these two bodies. So I'm going to call it Fg just for the heck of it, right? Force of gravity. Step number 2, identify any other forces that are acting on this thing. Well, if it's in space, I don't see any of their masses. There's no friction. There's no surface. There's no tension. There's no spring. So it looks like that's the only thing I got acting on it. So again, I'm going to go to Newton's second law. F, in this case, is the full of gravity, is equal to m. And m here is what's being affected. Well, it's the satellite. So the mass of the satellite times acceleration. And this acceleration is centripetal. Now it's a matter of plugging in, right, for the force that's doing the work. Well, this is g. Remember that? Big M, which is the mass of the Earth. Little m is the mass of the satellite over r squared. That's the force of gravitational attraction between bodies. Just a quick reminder. Remember, we always measure from the center of the planets, right? So you're measuring from the center of the Earth to the center of the satellite. These are called point masses. That force is equal to ma. And in this case, it's that magical v squared over r. That's that centripetal, yeah? Some things we can see very quickly. Significant. We tend to go by them mathematically because it seems so insignificant, but it's really very significant. We cancel the masses of the satellite. Really important. That means if I've got a P in space, or a BB, or a marble, or bowling ball, or the Hubble Space Telescope, the mass doesn't matter, right? The mass doesn't matter. What's important is how far out you are, how big is the planet, and how fast are you traveling. We use this all the time with NASA when we put things in orbit around Pluto, around Mars, the International Space Station. It's very critical. The other thing you'll see is one of these radii kill. So what are you left with? V squared is equal to G, big M, over R. So we could calculate how fast the satellite is going around if we know these two things. That's kind of important, again, if we want to put something in orbit. It tells us how fast we have to launch it. But notice where we started. Again, we drew a force diagram. There was an inward force that we identified as gravity, and we set it equal to ma. And again, we used our centripetal acceleration. All right? One of the things you guys are always freaked out about is, what about Kepler's laws? Well, here's the one that they're going to want you to deal with. Kepler's law talks about the rotation around this. So imagine this was a whole circle, right? Velocity is distance over time. So distance is the entire distance around this. I apologize for my circle, it's kind of gimpy. But the entire distance around this is called the circumference, which is 2 pi r. The time for one revolution has a specific name. We call it the period. And the period of rotation, or the period of revolution, is given the symbol capital T. So the derivation for Kepler's law says, look, take what you did with centripetal and just plug in here. Velocity, or speed, is distance over time. And it just so happens that the whole thing is squared. So you take it one step further, right? And you're going to get G me over r. And on this side you have 4 pi r squared over t squared. And I think the funny thing that they do with Kepler is they get all the r's on one side and they get all the t's to one side. And they get an expression. Let me change colors because I'm running out of room here in a hurry. You get something that looks like this. T squared over r cubed, right? I've just flipped this ratio, taken these two, and I'm going to take it across the other side, right? T squared over r cubed, right, is equal to 4 pi, right? I think I've got that right, over g times the mass of the planet. What's significant? Oh, that's the funniest squared I've ever seen. Sorry about that. What's significant about this is the ratio of the period to the radius that this thing orbits is equal to a constant. That constant, 4 pi g, that's the definite constant. The other constant is the mass of the planet, in this case Earth. So if this were Jupiter, or if it was something else, that ratio is a constant. It's kind of significant. But that's Kepler's law. That's the one thing that you were concerned about when you guys talked about gravity. I just threw it in here because it seems to fit this situation. Okay, that's example 2. Let's go to example 3. It's the one that's more pertinent to you right now. If I have a magnetic field and I shoot a particle into it, right? Here's a positive particle. Here it comes. Got a charge Q and a velocity V. When it enters the field, you're going to use your right-hand rule. The velocity is in this direction. The B field is into the board. So that means if you use your right-hand rule, your thumb will be pointing upwards. So that's the direction of the force when it enters the field. As this thing goes, if it's pulled upwards, that means that it's now going to be in this position, traveling in this direction. If you use your right-hand rule again, the force is in this direction. And if you follow this thing, what it does is it makes a circle, or semicircle the way I've got it drawn now. Bingo, immediately, in your mind you think centripetal. It's got a radius r. And you start with Newton's second law again. F is equal to ma. In this case, it's centripetal. Your job is to identify the force. What is the force that's acting inwardly on this particle to keep it in a circular path? What's it got to be? It's got to be our old friend, QVB. I've left off the sine theta because the velocity and the B field are at 90 degrees. M and acceleration is again our old friend, centripetal. And if I solve this thing for, let's say, r, to figure out how big the radius is going to be, one of the velocities kills this guy, and you're left with mv over qb. So you can tell again how big the path is if you know how big the particle, how fast, how much charge it has, and how strong the B field is. Again, this is the idea behind a mass spectrometer. But again, it's this circular path. Circular path, what do you go to? Immediately, centripetal acceleration, centripetal force. So that's one that we've done now. Let's give you another one that's a little bit more difficult that you might see. I've done this with a group of you. I think it was the SL when we went through some of our mechanics stuff. But let's say you have a ball or a cart or something that's going to roll down and go through this loop-de-loop. Well, as soon as you start thinking about this thing and you see a radius and you see a circle, you know immediately that this thing is going to have some centripetal acceleration. The place that typically problems like to look at is the very, 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 very top, right? And if you draw a force diagram for the very, very top, you have two forces. You have the weight of the ball, or the cart, or the roller coaster, or whatever you've got there. And you also have the push of the track, a normal force. Remember, a normal force is any surface. And that surface doesn't have to be horizontal. When the ball's over here, there's a normal force. When the ball's over here, there's a normal force. The cart is always, the track is always pushing against the cart, or pushing against the ball. All right, so if you look at this, you're going to get the same thing we did before. We're going to start with Newton's second law. And in this case, it's centripetal acceleration again. It's circular. You automatically default to that. What's the net force and where's the center of the circle? Well, the center of the circle is here. So these two guys are working together to hold it in the circle. So that's now my net force. And that's going to equal ma, and I'm going to use my centripetal acceleration. So you could find a lot of things from this. You could find out how big is that force of the track. You could figure out so much stuff. But one of the things they like to do is they say, they'll say, what is the speed? What is the speed if the ball or the cart or whatever just makes it around the circle? That just makes it around the circle means when it just gets to here, it actually starts to fall away from the track. It just barely makes it over. I think last year you guys had a bucket of water, or you had cups on a tray, and you spun it around, and you kept that thing in a circle. But if you started to slow down, you could literally start to feel the tension go and go slack at the top. You started to see the cups start to fall off. You started to see the water come out of the cups. What happens at that point is that the track no longer pushes. In other words, it just starts to leave the track. I'm going to exaggerate what happens here. It just makes it over and it starts to fall, right? That's if it's traveling too slow. If it just makes it around, as it starts to fall, it's moved around the circle a little bit more, and the track holds it in and keeps it moving around. So if they say it just makes it over, they're saying that the normal force is equal to 0, which means this becomes real easy. That dies. And look what you're left with. You're left with only two terms. And the other cool thing is, like our previous example, it doesn't really matter what the masses are. So if it's a big cart, or if it's a big ball sliding around there, or whatever, or it's a bobsled, or a roller coaster making a loop, it doesn't really matter the size of it. Look what you're left with. If I solve this thing for v, I get v squared is equal to g times r. What's that mean? It says I can find the velocity where it just makes it around this track if I know what planet I'm on and I know how big the circle is. If it's a really big circle, r is big, you better be moving pretty dang fast. If it's a smaller circle, you don't have to move nearly as fast. So one other example of centripetal force and centripetal acceleration that might be thrown at you. But again, we still followed the pattern. We drew a force diagram. We found out where the center is. We determined our net force. We wrote it in Newton's second law, and then we did whatever they wanted us to do. Okay? All right, one last example that might be illustrative of something that you might be able to use. They often like to talk about a hill. Yeah? So let's say that you're riding on a cart or a car, right? And you're going down a hill, and you get to the bottom of the hill, right? And you're sitting, pardon my art here, guys, but you're sitting in a seat in this car or cart. And they want to know, what do you feel? When they say, what do you feel, they really want to know what the normal force is, right? And the normal force really is the force of that chair pushing up against your butt, right? So we're referencing everything to you. So here you are sitting in your chair, and let's look at you at this point at the bottom of the curve. First and foremost, it's a circle. First thing in your mind should be, okay, it's centripetal. Let's get to work. Next thing you do is you say, okay, let me draw the forces acting on it. Well, weight is certainly acting down. That's one thing. If that was the only thing, you would fall through, so there better be another force. That other force pushing up on you is the normal force, right? So you got two forces acting on you. And if we ask about, how do you feel in your chair, or if you're sitting on a bathroom scale, what would it read is another way for them doing it. What you're going to do is you're going to set up Newton's second law. Now, first and foremost, figure out where the center of the circle is. The center of the circle is up here, right? Right? If I'm going around this circle, the center's up here by my head. So now we need to use Newton's second law. And if I'm being held into a circular path, that means this force is winning the tug of war. So its normal force is beating mg. What kind of acceleration? We have centripetal, so that's equal to m times a. In this case, it's v squared over r. And so if we're trying to solve the normal force, or the force that you feel pushing against your butt as you come down this curve, we'll solve it for the normal force. And look what we get. We get mg is plus mv squared over r. So if you've ever been on a roller coaster that goes down a hill like this, and you come to the bottom, you feel like you're being pressed into the seat. Well, that's your reaction. That's your human reaction, right? You're not being actually pressed into the seat. What's happening is this normal force has to be bigger to hold you in the curve, because not only does it have to fight against your weight, but it also has to fight against the fact that you're traveling, and you're traveling pretty fast. So to hold you in that curve, the normal force has to be larger than normal. So you really feel heavier, or you feel like you're being pushed into the seat. It's the reverse. The seat is pushing up into you to hold you into the curve. The converse is true when you come over the top of a hill and you're traveling very fast, and you're in that same roller coaster, and you're sitting in that same chair, right? And the question is, again, what kind of force? Well, even though you're on the outside of the curve, there's still a radius, it's still a circle, nothing changes. The first thing you do is you draw your force diagram. Your force diagram looks sneakingly similar to what you just did. You have mg down, you have a normal force upwards. What did we do next? We said, okay, let's identify the center of the curve. Well, the center of the curve is here. So that means there must be a net force towards the center. Well, on my force diagram, that means this is the center down here. So who's got to be winning the tug of war now? If they're not helping each other and they're fighting, the net force is going to be mg, the thing that's winning the tug of war, holding it to the center, minus the normal force. That's our net force now. And it still equals mv squared over r. There's our centripetal acceleration. Now, if I do this, it's a little bit different. Oh, sorry, I left my n off here. Now it's a little bit different. If I look at this thing now, if I solve it for the normal force, I get the normal force is equal to, and if I take everything across the equal sign and make everything positive, because I know you guys like positives, it's going to be mg minus nv squared over r. Well, look at the difference. There's a minus sign. Yeah, okay, I get that. But look what's happening. We're taking away from our weight. In other words, as you go over this curve, the normal force gets less and less and less. You feel like you're floating because the chair doesn't have to push up against your butt as much to hold you in the curve. Gravity is doing the work. The normal force is actually doing very little. What happens when the normal force goes to zero? In other words, your butt leaves the chair, right? You're starting to separate from the chair. Well, if this goes to zero, it looks really familiar. mg is equal to mv squared over, I've seen this before, like an example ago. The mass is canceled, and if I solve this thing for v, I get the same thing I think we got before. If I know what planet you're on, if I know how steep this curve is, right? If I know how big the radius is, I can tell you the velocity before you leave the chair. Also, before the car leaves the track. So it's kind of important. If you have a really, really big radius and you're traveling very fast, that's what they want in an amusement park. They want you to feel like you're leaving your seat. Of course, they got a bar there to hold you in. If you're in a car, right, and you're coming over a mound, a hill too quickly, Your car can leave the surface, then you launch, right? You end up going off and flying off. Or you feel like you're leaving your seat, which is not a good place to be if you're trying to drive a car. So, bottom line is this. We've shown you, what, 4 different examples, 5 different examples? They've all started the same way. Draw the force diagram. Identify the center. If it's a circle, you're automatically taking this route. Identify the center. It's winning the tug of war over the other force. Set it equal to MA. And then whatever thing else they want you to find, you find. I think that's probably all I can do to help you out on this particular section. Again, they typically use these to find velocities or forces so that you can solve something else about the problem. But they all, again, generate the same way. One last thing that just might be useful, just for the heck of it. If you've got something traveling in a circle, and I'm jumping a little bit ahead before I get to energy, but I at least want to say this. If something's traveling around a circle, one of the things you're going to be asked, and you need to know why, is they'll say, how much work does the tension do, or does the centripetal force do, holding this thing in a circle? And the correct answer is 0. It does absolutely no work whatsoever. Part of the reason is, if you look, the velocity of this thing is in this direction. And you know that work is force times displacement, right? Well, it's hard to see here because the displacement, if I go from here to here, right, that force is always tangent to the, is always perpendicular to the velocity. So that's one indication that the work is 0. But there's another thing. There's a really useful equation or a concept that was told to you last year that most people forget. And it's, if you do work, you change the kinetic energy of something, right? So look at this example. If this guy stays at a constant speed all the way around, how much have you changed its kinetic energy? Well, you haven't. So if the kinetic energy is 0, that means the work that this tension did was also 0. The only goal of the centripetal force, the only goal of this tension, is to change the object's direction. It doesn't speed it up, it doesn't slow it down. It's kind of like what I told you about a magnetic field. A magnetic field changes the direction of the object, but it does not speed it up or slow it down. Solely there to make it go in a circle. Okie dokie, that's it on this one, guys. Hope this one helps.